a talk in Berkeley on computational metaphysics roughly 2 years ago. And it was organized by Dana, and in that talk I presented our work, the previous work on the ontological argument for existence of God, and I showed him that his variant of the argument was better than Gödel's because Gödel's had an inconsistency in it, at least the one we found in the Atlas. But I was surprised that Dana wasn't at all so much pleased by that critique. In a sense, yes, but he was more interested in how I actually use the system infrastructure, Isabel Hall, to deal with the logics we needed for these experiments, namely higher order modal logic. So in a bit less ambitious logics than Daniel worked with, it was the classical extensional higher order modal logic. He worked with intensional, but he got interested in that, and he said if you can do that well with that infrastructure, then you could do what I was always interested in, namely implement free logics with the same idea. And I said, what is free logics? I didn't know about that. He said, okay, let's sit down and explain you that. And he said that's a really nice and actually very well suited logical framework that might also have a role in foundation of mathematics. Why? Because it's dealing with the notion of causality and undefinedness in a very elegant way. So that's the motivation here. So he was motivated to get free logics running on the computer, and then he said, well, once we have that, we can do very nice experiments in different areas of mathematics where this exactly plays a role. And he said, let's then start with category theory. So that is the background story for this presentation here. The rough structure, I first say a bit about the technique. You have already seen a bit of that in the talk by Daniel, universal reasoning by exploiting the idea of having a meta logic in the background, and this in this case classical higher logic. This can possibly be exchanged by other formalisms. So we stick to higher order logic for the moment because of pragmatic reasons, degree of automation we can achieve. And we achieved that idea of a meta logic here with exploiting or utilizing the idea of shallow semantical embeddings. I say a bit of that, or addressed it a bit in the first part. Then we come to free logic, and after that I show you this exploration of axiom systems for category theory. And if you have time, then we can reflect on these experiments in the last one. Here's a quote I put together for Henk. We talked about the table, and this is actually a quote which is motivating my work since quite some time. Quote by Leibniz, letter to Valois in 1677, and he said, if we had it, a characteristica universalis, we should be able to reason in metaphysics and morals, so philosophy, ethics, in much the same way as in geometry and analysis. So he was dreaming of this idea of a universal reasoning approach based on a universal logic. But if you look at what we have achieved, or I'll do it in a second, so if you look at the situation right now, yes, logic is important in many areas out there. Mathematics, of course, we're still questioning what could be the right foundational system to consider here, but there's more than mathematics, so logic plays a role in more or less all the sciences, and even in our, let's say, social processes in the world out there, because it's foundation of rational argumentation. And but if you ask, I'll come back to the quote of Leibniz, then you see that instead of having this one logic, we are actually dealing with very, very many different logical approaches, in particular in these different areas. If you look into philosophy, you have an interest in, let's say, modal logics, higher order modal logics, second order modal logics. If you, in other areas of computation linguistics, you might have an interest in other logics than, for instance, if you consider the foundations of mathematics. So what we have, instead of this characteristica universalis, is a logic zoo, a rich zoo of different species in there, and some of these species even have very rich subspecies. Think about modal logics, for instance. Nevertheless, what we achieved now in joint work with colleagues in the last years is different formalizations of work in different areas within a single mathematical proof assistance system. And that is because we use this idea of exploiting a meta logic in which we then encode these other logics which we needed for these studies. This is I briefly address now a little bit more in the first part here. So how do we do that? If I actually enter now a new challenge in philosophy, or let's say now recently I'm pretty much concerned with legal reasoning, then I face new logical systems that are considered in these communities. So what is the first step to do? You look into the books or textbooks that are written by humans about these logics. And in these books then you find first exploration of the logic itself. So you have a meta language, and in this meta language, then you typically introduce the notions of that new logical system you're talking about. That's what we in computer science at least do in many, many papers. Then on the next pages, typically find a description of the semantics. Like here, flipped style semantics for a multimodal logic in this case. So why not exploiting exactly this idea in a systematic way and read off the semantic descriptions of the logic we are dealing with and translate them, try to translate them into equations in a meta logic. And in the work I'm doing, I'm typically interested in shallow semantic embeddings of these logics. So here in the case of modal logics, we have a dependency of these possible word structures. So our formulas are now, the interpretation of formulas are now depending on words. And exactly this idea we can now simply express in the shallow semantic embeddings by lifting propositions to predicates. So we explicitly talk about this dependency on words. A very trivial idea. That's also what you do in the standard translation. But if you look at that from the perspective of higher order logic, then you find that you can easily extend this idea of the standard translation in this case to work also for quantifiers, because we use the big pi, and the big pi can also be lifted in that way to work on propositions. So you get an embedding for higher order modal logic more or less for free. We could explain that now on here on a blackboard or so, how that works for the quantifier. But that was an intriguing fact for me, that I can deal with the same way, given a small set of equations, in this year 12 equations, which deal with the propositional case of modal logic and also with the quantificational aspects of it.
Church would say, once you have a lambda, you can do it there and you can do it there.
Yeah, exactly. That's the point. You have one lambda in the background, the only binding mechanism you use, and you exploit that over and over again. And that is very powerful. And that is actually the reason why I like Holl for the moment so much at the meta level. You could eventually replace Holl by another formalism, a set theory base, or so on, which eventually has the same expressive power, but you wouldn't have the lambda inside. So that's what we do. Take Holl as a meta logic, and then try to come up with a shallow semantical embeddings in the sense of these few equations you saw in the last slide in Isabel Holl, and then encode in the previous slide that was a higher order modal logic in classical higher logic, and then you exploit that for applications. We have done that for a whole range of different logics meanwhile. So I've worked with intuitionistic logics, with conditional logics, with interesting logics. Daniel presented this work on hyper-intentional higher order modal logics. At the moment, I work a lot on dyadic deontic logic and input-output logic that are relevant in legal reasoning in particular. So here I said it, the motivation for sticking to Holl for the moment is that these systems we have already developed over decades now, like Isabel Holl or Holl 4 or Holl Live, PBS, and so become readily available for such experiments. I stick to Isabel Holl because it has a good degree of automation in there, and I can connect easily to my own geoprogrammers, for instance, Leo 2. And Isabel has nitpick. Model finding is very, very good. And you will see that in the experiments, it helped us a lot to have the model.
I think this would be
nitpick. It's a model finder. It can give you counter models to statements. So that is the technique we use, and now I come to this part about the logic. What's the motivation here? Free logic, typically the name you find in the literature is Lambert, but Dana Scott also wrote a paper about it. You see it here, that was in 67, existence and description and formal logic. And the motivation here is as follows. There have been three major suggestions on how to treat descriptions, definite descriptions, usually associated with the names of Russell, Frege, and Hilbert Gardner. The author does not consider any of these approaches really satisfactory. So it really was designed to deal with the notion of undefinedness, and in particular in the context of definite descriptions. So I'll give you a bit of these motivations. Look at this nature language example. The present king of France is Francis Bald. Russell would propose in his first approach that this actually stand, if you try to formalize it, and let's say we introduce this predicate, present king of France, then we would say the term, or the formula, Bald, that X, which is the present king of France, should actually be rewritten into that statement here. So it has an existence condition, a uniqueness conditions, and then here comes the baldness condition. Okay, hence that would evaluate to false because existence conditions would not be satisfied. Now, Frege says that term, that X, which is the present king of France, doesn't denote. Hence, this formula, Bald, that X, present king of France, X has no truth value. Also not a very satisfactory approach. And Hilbert-Bernheis would say, well, you don't even consider that term part of the language if you can't, at, let's say, parsing time, prove an existence and uniqueness condition. So here's the alternative approach in free logic. Free logic says we now distinguish between a raw domain D, that's, let's say, the typical first order domain you consider, and a subdomain E of the existing. We talk now explicitly about the non-existing. So in the domain we have now objects that characterize the non-existing, but we distinguish between them by introducing this subdomain E. So principle 1 is now bound individual variables range only over the domain E, so the subdomain E of D. So whenever we say something like for all X, then we mean the objects in here. If we have arbitrary terms of free variables, then they range over D. So they could denote, but they could also denote the non-existent. And then there's this kind of optional principle here. The domain E might be empty. I mean, usually we consider quantification over non-empty domains.
Oh, so, Chris? So the domain E, can I imagine it like types that are non-empty, basically, that you have some non-empty?
It can be empty. E can be empty.
Oh, okay.
Yeah. It can be empty. There are different variants of free logic mode. Okay. You might say, oh, I want to consider a case where it's non-empty, and so on. Okay. If you look into the literature, you find different variants, but it can, in principle, it can be. Okay. Now that, unfortunately, the resolution is not too good. That can be now easily translated. These ideas of quantification and so on can easily be translated in Isabelle Hall. I mean, most of you have done formalization work. You won't consider that as a too ambitious thing to do. For instance, the universal quantifier is now simply restricted by this guard E. So we introduce an explicit predicate E that's denoting the existing, and we guard now the universal quantifier by that E. Isabelle Hall allows you in a very nice way to introduce new syntax and even new binding notation. So I can have now the bold-face binder as the new binder for free logic, and it's actually discarded binding mechanism. This is the underlying binder in Isabelle Hall. So that's very convenient. I can introduce nice new syntax, and it's convenient for the user. And the same you can do with the description operator. So the description operator we were talking about before now becomes gets the following definition here. So that X, which has property phi X, is mapped to this this term here, or this formula. If there exists an X, and the exists here is the underlying existence quantifier in the background, so ranging over everything. If there exists something which is existing, so in here, and has property phi, and is unique, then we return that X which is existing and has property phi. And that is the description operator of Isabelle Hall in the background of the meta. Otherwise, we map it to undefined. And again, we can introduce nice binder notation. So now we have a nice description operator redefined using the existing one in Isabelle Hall. But I mean, description is not really relevant for the rest of this talk. We don't even use it. I just wanted to show you what you eventually could do in other areas with that framework. And that was the original motivation, one of the core motivations. So now we come to this explorative study in category theory. So Dana said, There's never been implementation of free logic. You can do that very nice. Now we go and see how far that scales with respect to automation in systems. So let's look now at one area that requires treatment of partiality and undefinedness in an elegant way. Category theory is such an area. So here is the idea or the experiment Dana proposed. So he said, well, I have this paper out there on category theory written in '77. And he proposed in there a set of axioms for category theory. And he had the idea now to work out a connection of that paper to a kind of generalized notion of monoloids. That was the challenge. He wanted, let's try to find a generalized notion of monoloids and then walk step by step towards this axiom set I presented in '77. So let's make a nice connection to structures we have already explored. And then when we can do that, then he said I always wanted to compare my axiom set with the axiom set that was presented by Fried and Petar in the textbook they presented in 1992. And try to find out whether all of these axiom systems are equivalent. That was the layout of the experiment. We exchanged hundreds of emails and worked together. So it was a team, me as kind of tool expert, Dana as the domain expert, and Isabel as the assistant here, the work of our sense. So here's now the idea of how to model these notions of category theory here in the framework. Morphisms are becoming now objects of the type I, and the type I will be associated with this raw domain D. Okay, can actually we have elements of which are considered as existing, defined, and elements in there which are consisting of denoting the undefined. So then we can talk about later of these partial functions, dom and codomain, dom and cod, and of course of composition of morphisms. And they can be handled now as expected as partial operations. So for instance, you can say that the composition of two morphisms A and B may be non-existing in a case where you have existing morphisms. So the composition of A and B might well be denoting an object outside of B, even though they are existing. Now, very important, I haven't talked about equality in context with free logic yet. Very important is that we can now introduce different notions of equality for free logic. And one is Kleene equality. Kleene, and this is relevant for the rest of the talk, these different notions of equality. Kleene equality, you know, is as follows. So x and y are Kleene equal if and only if we have the following here on the right-hand side. So either x exists or y exists, and if that's so, then this implies that they are identical. And this here is the identity relation on D, on the entire domain we are considering. So this is an equivalence relation on D, on the entire domain D. And this is a different notion of equality, existing identity, which is not an equivalence relation. Existing identity is defined as follows. It says x and y are identical according to this notion if both exist and they are identical. So it's restricting it to the existing, the notion of identity, and outside it's the empty relation. So you have this here, for instance. This existing identity is an equivalence relation only on E, and it's the empty relation outside E. And that means it's a very interesting notion because now you have that 1 divided by 0, for instance, is not the same as 1 divided by 0. So you are not identifying the undefined. Or you have 1 divided by 0 is not the same as 2 divided by 0. And you also don't have that the present king of France is the same as the present king of Poland. Those are non-existing, but they are not the same.
Whereas for the Kleene, they would be equal.
For the Kleene, they would be equal. Kleene is an equivalence relation on entire D. So, but now we have two notions of equality, and we can use them as we need them. So now we start with the notion of a monoloid. Remember the experiment, so we are up here, and well, you all know the notion of a monoloid. The idea is now to make that notion, to somehow partialize this notion. So we have a closure condition, associativity, and then two-sided identity element here. And now we come up with our first proposal. Actually, that's not the way we proceeded. We went back and forth from the given axiom system. That's clear. But here I've chosen now just a forward presentation of that. And that is now the first axiom set we come up with. So compare it with the structure of a monoid, the closure conditions are now replaced by strictness and existence conditions. So in this direction, we have a strictness condition, and in this direction, an existence conditions for the composition of morphisms. Associativity is still there, and remember that the free variables here range over the entire domain, so including the undefined. Now here we strict the identity statements become the axioms C and D. So talking about what we later call COT and DOM, domain and codomain of morphisms. And here they are stated as follows. So for all existing Y, the existing I, which qualifies as an identity morphism in the existing area, and then has its identity property. And analogous for the domain. Identity morphisms are characterized as follows. It's written here. And you see, it's not so easy to get an intuition for these formulas, and you need to play with the systems to really sharpen your intuition for it. We did that at the Thrive here with Daniel for a long time, find exactly out what these axioms do, to give you a little bit more of the intuition. What you can prove actually quickly, Sledgehammer tells you that the I in axiom C is unique. You have a unique one which is fulfilling this codomain condition, and this we later call codomain. And we have a unique element which is fulfilling the domain condition. That is the one we later call DOM. And here we have a statement that's actually requiring, and it's really surprising that it does it, that they are coinciding. So for the existence of a composition of morphisms, we want that the domain and codomain of the operation coincide. And this part here actually does it. It's surprising that it does it, but it does it. So that's giving you a bit more intuition behind these formulas. Well, and with experiments, looking at the models, you can dive further into it. We worked a lot in collaboration to find the right formulation, for instance, of the identity predicate, in combination of the right formulation of codomain and domain, and this condition. So now we step forward. Now, okay, a little bit more about the experiments of Isabel Hall. So Isabel Hall tells you directly that, for instance, you can avoid the other direction here, so that you get for free in the other direction. And Nitpick tells you that this axiom set is consistent, and it tells you that this axiom set is consistent even if we assume that there's at least one non-existing element, so that we indeed may have partial compositions. That is important also for later, because the axiom system of Wright and Scatroff has a problem with that. So yeah, remember that we do this experiment now always twice, not just asking for consistency, but also consistency under the assumption that there's at least one non-existing element. Here you see a little bit of the communication with Dana. So here we were actually puzzled by the right formalization of this identity predicate. So here I said, when we take IDD as this one here, that is actually the one you saw now on the previous slide, and replace ID, that was the previous one we had, and our axioms we consider so far, by this new proposal, then I can show that both are equivalent. See the attachment, and I always send him these pictures from Isabel or handmade pictures and so on. And then Dana responded, I'm surprised, because I did not see how to prove this statement here. The idempotent follows. I have to think about it. I hate it when computers are smarter than I am. I guess C and D have to be used. And I wrote back, hi Dana, I see the first attachment of my previous email. C and S are used for this. It's called IDD help 1. And so that was the style of communication we had over weeks in all these stages of the development. Here's another one. Dana asked me a bit of context. Please check that, therefore, whether this is provable from the S axiom. So he gave me this exercise. Ask the theorem prover. And I wrote back, first of all, here the results doesn't look too good. Apparently, it isn't. See attachment. Counter model is presented in the lower window. We have this one. And typically, I was presenting him these counter models then in a more natural way. That nitpick should do that. Nitpick should actually give you this representation. That helps a lot. And here you see that's an interesting one. You have idempotence, but you don't have existing identities. That was an interesting model to look at. If you want to get intuition, that's an interesting one to study. Okay, unfortunately, so we don't have the time to dive now more into experiments and so on. I can give you live demos, and so when you're interested, we can play with it and you can try to question the axiom systems. So now we move on. We go to axiom set 2. That was the previous one, that's the new one. Now we do want to get rid of these quantifiers in here. So the first thing is to think about spolemization in these two cases. So we introduce spolem functions, cot and dom. So we name them cot and dom, and unfold the universal quantifier. That's where this guard here comes in. When doing that, we find out by experiments that we have to sharpen the strictness condition here and also require strictness for these new spolem symbols. And now we can prove that the axiom set 2 implies axiom set 1 and sledgehammer does it automatically. The other direction is a bit more problematic because we did here introduce column constants with the model change, and I don't see a way right now how we can do that fully automatically. That's the only part in the exploration where we had to argue by pen and paper that this is correct. That's the only. Okay, but maybe that's also possible. I haven't probably thought sharply enough about it, how I can do that within the metalogical system So now we move on, axiom set 2 to axiom set 3. We go stepwise and try to, produce a nicer, cleaner presentation of these axioms. We want to get rid of the existential statement here. So now we have now these new column symbols, cot and dom, so we insert them here. I said before, this here is giving me a surprise, this kind of identity between cot and dom of x. And so we can replace that by this clean inequality in combination with requiring that one of the two sides actually exists. You also get for free that the other side exists. That's what we do. And then again, you can now use the theorem provers. Sorry, that was quick.
So there you despise the quality of the beginning.
Yeah, that was the clean. We use now the clean equality here, but in addition require that one side exists. So basically, I should be able to replace it also by existing identity, and that's what we will do later. That comes, right? Yeah, but that is relevant for the Freud and Spektrov, because Freud and Spektrov don't use the existing identity, and I think that's a flaw in their system. And there you see the motivation for first presenting it like this. So now you can do experiments again. Consistency, also when you require at least one non-existing element, left to right direction of this statement is implied, and you can prove equivalence between the axiom sets 2 and 3 automatically by sledgehammer. Very nice. No interactive proofs needed. That would be now the point to give a demo. As I said, whoever is interested, I'm happy to sit down together and show all that. And also to work with counter models to get more intuition. And I mentioned this model here before. Now the next step is to further simplify axioms cot and dom here. And that can be done. You can simply replace these here by these statements. When you sharpen the existence condition here in an equivalence statement. So if you do if you add that, we have now here an left to right direction as well, then you can replace this by this here, because you now ensure the existence condition you need to think a bit about it. Again, you can prove that those two axiom sets are equivalent, and you get consistency. Now the last step to the axiom set proposed by Dana Scott is to replace what we mentioned before, the Kleene equality here by the existing equality, and to get rid of this existence state. This is the axiom set Dana presented in his paper in '77, where he precisely said, and I assume now here, free logic. So very clean paper. You say exactly what the logical context is, and then you provide this axiom set. Okay, we get again experiments confirming the equivalences. Now, again, that would be point for again. We skip it. Now, I mentioned that we are here. So we have done this exploration. We have a nice confirmation for the axiom set, and we have linked it back to a notion of generalized monoids. But now we want to find out whether there's a connection to the axiom system that was proposed by Fried and Skatrov in the very beginning of that book. So that is just a kind of initial experiment. Actually, Dana wants to look at the entire book now and see how far the automation scales and so on and what we can do. But we haven't continued so far, mainly because I had to do other things, and would be a perfect project now for another PhD. So the challenge here is, let me go back to that slide. The first challenge is that Fried and Skatrov use a completely different notation. So the box and the box on both sides of the morphisms here representing Cod and Dom, and I think this is Dom and this is Cod. But the more challenging thing is that this notion of composition is just a reversed one. And this is really a challenge to first translate this axiom system into the other one. If you just think in both systems in parallel, you get completely confused. So that is the first thing you need to do. You have to translate the presentation of Fried and Skatrov in the notation here. And this is the axiom system when presented in the notation by Dana. So now I did first some experiments and asked about consistency, and nitpick tells you, yeah, there's a model. But then when you assume, important, now we do these experiments in the same logical setting proposed by Dana. We assume free logic, and we assume that the variables are ranging over the entire domain D, including the undefined. Later we will change that, because in algebraic theories, you very often say that the variables range over the existing only. And we can do that because we have this nice universal quantifier of free logic. And we can put that just in front. So first, we do our experiment with the interpretation in free logic of that axiom system. And later, we change to an algebraic interpretation. In that context of free logic, we ask for consistency. Nitpick tells you there's a model. There's even a model when we assume that there is some non-existing element. No, there's no model anymore. That's the important point here. So if we now assume in that setting of free logic that there is a non-existing object, then to my surprise, nitpick didn't find a model. And then I tried to prove that formula here from the assumption of a non-existing element, you can show falsity. And Sledgehammer does give it to you directly. Very interesting. And it tells you also what the problematic axioms are, A1, A2A, and A3A. And you see here the problem. There's a clean equality.
Okay. There is a question over there.
Yeah.
You said nitpick does not find a model, but prior to that you said there isn't a model. Is nitpick not finding one?
Nitpick says you there is no model, meaning there's a finite.
Does that mean there isn't one, or there's
if nitpick tells you there is no model, it's a finite model finder. That is one of the suggestions I have to just run. It should be very precise in the result. It tells you I didn't find a finite model. But then to make sure, but it's not considered a verified statement in Isabelle Hall, so it's better that you have an explicit derivation of falsity in this case. And that's exactly what I tried then. And the Sledgehammer, the tools, and Turing Progress tell you.
Oh, I said point 3.
Yeah.
Sorry.
So when interpreted in that context, free logic, then the axiom system of Fried and Skatrov seems to be flawed. So either all morphisms exist, that means we have a total composition of morphisms, composition operation, or the axioms are inconsistent. That's for sure not what is meant. But when you now, in the experiments, replace this Kleene equality by existing identity, then consistency is confirmed also for the case of a non-existing element, and you can now prove equivalence to the axiom system of Scott. Very nice. And again, the Turing provers do it. But you find redundancies. The A4 axioms are implied, so you can either delete those two here, or you can delete the A2 axioms.
Can you also delete one of each? Can you also delete one of each?
No, I don't think so. I think it's just those, but these are typical experiments. You could now do an exhaustive experiment. What are the minimal sets? I think I did it and I have it somewhere, but these are two obvious choices. And I think it would be the A4 axioms was the bigger in sense and composition.
You're into your question period.
Oh, okay. Yeah, but we are more or less at the end. So now we do the final experiment. We say, oh, maybe Freuden's-Petrov did actually mean that the variables are ranging over the existing only, like you often do in algebraic context. The book doesn't tell you that. The book doesn't say what exactly the three variables are ranging over. But we can do that experiment here as well. So we just put the quantifiers now in front of it. Now they are running only over the existing. If you now do some experiments, then you can see that consistency holds, but none of the D axioms is implied. So you don't get the equivalence to this axiom system by Dana-Scott. But if you add strictness conditions for Dom and Cott and the composition operation, then you can do it. Okay, so strictness is missing here. So, but now consider it. Strictness is not all mentioned in the book by Freuden's-Scott. They don't give you the logic in the very beginning and say this is the logic we mean, and we mean that all our functions are strict. And now assume, and the point here is it could not even be expressed axiomatically when variables are assumed to range over existing objects only. At least I didn't see an elegant way to do it. And then Dana said that needs to be kind of puzzled about this axiom system. So it should eventually be the case just use here the existing identity and interpret it in free logic. And that was then hence to better prepare the axiom set by Scott. But you see, Dana had a motivation here for the experiment because it can show that this axiom set is very clearly presented in a precisely state methodological context. So we could offer now some reflections on these experiments, but I would say I leave that to the questions. The most important thing is only this one here. I think that we should think about how we could first eliminate my role in these experiments, because I think I was not really needed. It was an interaction between a proof assistant and Dana-Scott. He had the intuition. I mean, I contributed a little bit when we came up with some of the axioms and so on, but it was more or less something that the domain expert should be able to do it without any middleman there. But he tried in the beginning to learn this a bit, but it was still too hard for him to really do this kind of thing. There is some background knowledge needed, especially what it means when theorem provers come back and one theorem prover tells you error, really with an error message, a bug in there still, and this may happen. Or you might have even controversial feedback, and I mean, you have to know a bit about these systems still to interpret them correctly. Or when nitpick tells you there is no model, meaning there's no finite model, and so on. And then one might think of in this community how to get rid of the domain experts. I mean, that's exactly what we were talking yesterday in the panel discussion. How can we find the criterions for these different axiom sets when we consider them as the beautiful ones, and so on? And here you have a couple of these axiom sets now, which at least Dana and myself now consider as beautiful. Well, yeah, I have more to offer in that regard, but I think we can leave that for discussion. Let me this one.
Very much.
Questions?
How did Freud and Petar react?
We had emails with them, but before we really fully understood the problem. So there's more to the story here. So first, I was playing when I had free logic independently of this, let's say, controlled interaction with the domain expert Dana-Scott with just the axiom system by Freuden's-Petrov, and I found redundancies first. But at that point, I couldn't really interpret them well. If you read our ICMS paper, which we wrote early in 2016, that was at the stage when we hadn't fully understood the connections. And you find in there that we reported we found other redundancies as those that were known, and these were actually implied by the inconsistency. and we didn't fully understand the entire thing at the first place. So in that phase, we communicated with Fred and Sketchrock early on, and then Dana said, "Oh, we have to now look more carefully into that." And afterwards, I think we sent them the entire work, but there was no big discussion anymore. So I think the book, I mean, you could argue if you interpret them now in a setting where you assume that the algebraic theory that the variables range over the existing variables only, then it's only a minor flaw, because you should have said somewhere in the beginning that you assume that strictness is given for all the functions fine. But that's not apparent for students, I think. Or you assume that this book is read in a context where everyone knows it, but I would doubt that if it's meant to be an introductory textbook. So I think the flaw can be considered as minor if you read it in that context. If you see it in the context of free logic, it's a major flaw. And so I think there's not much need for communication on that. And nevertheless, it would be interesting to see how they would respond. But I think the response will be, oh, we assumed exactly this logical background, and we don't talk about these things in mathematics. And that's my criticism. A mathematics textbook should very precisely say what the logical context is.
You say that Sledgehammer did most of the things automatically.
Yeah.
So if you got a proof, a Sledgehammer proof, did you feel an urge to look into the proof and understand?
Yeah, sure. I have a fully intuitive version of the inconsistency we could now go through. This is the inconsistency argument, very tiny. You all understand it in a minute or so. And this is the one in the formulation by Dana's work. Yeah, so I did, these things can be done. And the theorem provers very often give you already, there are reconstruction mechanisms which try to reconstruct proofs in the ESA-like presentation. And very often that was already quite good. There's still room for lots of improvements.
Okay, I think we need to move on to the second speaker. Let's thank our speaker. Our second speaker is Petar Vukmirovic.
Okay, so as disclosed, today I will be talking about something a little bit different. So I will be talking about implementation aspects of extending first-order theorem prover to a richer fragment of higher logic. So automatic theorem provers, as you might know, are tools that are used to prove theorems without any user's existence. And the current state of the art is that first-order provers are much more mature and faster. However, they are based on less expressive logic. On the other hand, higher-order provers, even though they are very advanced, they are less mature and thus slower, but they are based on much richer logic. Our challenge is to reach high-performance higher-order theorem prover that extends first-order theorem proving gracefully, which means that it keeps all the nice properties that first-order theorems provers have, most notably their performance on first-order problems. So my approach to this problem isn't building a higher-order theorem prover from scratch. So it is starting with a first-order prover and then extending it to a slightly richer logic step by step by adding higher-order features of which we understand both syntax and semantics very well, and hopefully reach fast higher-order theorem prover. In this process, so this optimization step has twofold importance, because it is very important to optimize what you're adding, but it is also incredibly important to make sure that the overhead that you're adding to the existing reasoning core is very small. So without any further introduction, I will talk about the richer logic that we support, and our logic is typed and single typed, and the terms are built as either variables, function symbols, or application of one term to another one. In other words, the features that we currently support of higher-order logic are applied variables and partial application. Together, those two features constitute what's called lambda-free higher-order logic. So the logic that is different from first-order logic in only supporting those two features, so applied variables and partial application. Previously, I've shown you the general framework in which we have set our work, but in particular, we extended first-order theorem prover E to this lambda-free higher-order logic segment, and what we reached is a prover called higher-order E, or quote, if you like. The first thing that we had to generalize when extending E to this richer logic was the internal term representation. So, of course, since E is the first-order prover, it doesn't support features like partial application and applied variables natively. So we had two different approaches. We could either change internal representation of terms, or we could encode this using traditional implicative encoding, where we represent a term application as a distinct binary symbol and make every other symbol a nullary. And let's see what are the pros and cons of both approaches. Well, the first approach is very memory compact because we don't load terms with additional symbols, and it is fast for very elementary operations. For example, looking at the nth argument of a term is done in a constant time, whereas for applicative encoding it will be done in linear time. And it works nicely with the existing E code because a lot of times you would look at a term head, and in the native representation, the term head would always be what the term head really is, whereas in applicative encoding, almost always it is going to be this artificial application symbol. On the other hand, applicative encoding has one very nice side, and that is that there's pretty much no work to be done. You can change almost zero E code and just implement a preprocessor that is going to encode everything using applicative encoding. Because of the all advantages of native representation, we chose to go with it, and this had many implications, as you will see later. One of the first ones is that all the algorithms and data structures, well, almost all of the algorithms and data structures that a first-order theorem prover works with had to be changed, including unification algorithms. So, yeah, as all of us know, so the unification problem is problem of finding a substitution that is going to make two sides of the equation equal, and more generally, we can do this for the set of equations. So, first-order logic unification algorithm. The standard Robinson one is very simple. We just remove. We start with the initial set of equations, and we remove one by one where we can, and then we perform some transformations in that set based on the equation that's removed. This transformation is the most important part of the algorithm, and I will just quickly go through it. So, based on the equation that's removed, it can be the case that the head of the both sides are the same. In which case we recursively try to unify the arguments. It can be the case that the heads are different, in which case we report failure, and then we can have the case that one of the terms is a variable. In which case we would like to standardize the situation a little bit, so we would like to have variable always appearing on the left-hand side. So we perform some reorientation, and then everything is straightforward. So if the variable doesn't appear in the term in which it has to unify with, well, we just apply the substitution. If it does appear, we report failure, and if it has to be unified with itself, we just ignore this. However, this algorithm would fail on lambda-free higher-order terms. The reason for that is, so suppose that we have unified this equation, and first-order logic algorithm would just say the heads are not the same, and I have to quit. However, there is a unifier, and if we substitute x with fa, we would get the unifier. Now I'll show a little bit more involved example that is going to give us the feeling of what are the generalizations that we need to perform in order to have a unification algorithm. So in the superscript is the number of arguments that a variable can be applied to, and it is should be clear that since the variable x can be applied to 2 arguments, and on the right-hand side, f is applied to 3 arguments, if I supply 1 argument to f, and if this type checks, then I could bind x to f of a. And this operation we would call prefix matching. So now variable doesn't have to match the whole term. It might match a prefix of the term, and we can determine this using typing information and areas. Similarly, now variable y, since it is applied to 1 argument, can match zb. But again, we would like to perform some standardization, so we want a variable that can match something to appear on the left-hand side. Thus, we have to generalize the reorientation. And now when I reorient, I can perform the prefix match that I told you about recently. So y can be matched to zb, and now we are left with 2 simple unification problems. And after 2 decompositions, we get the unifier. So this is an example of what are the new cases that emerge, and this is the generalization of the first order unification. So the new cases appear when we have variables as the heads, and so other cases are pretty much the same. So I can hide them, and also if neither left-hand side or the right-hand side are applied variables, this is also the same case as in first order logic. And now we have 2 new cases. We have to generalize their reorientation if the right-hand side is applied variable and the left-hand side is not, or if the right-hand side is a variable and the left-hand side is applied to more arguments than the right-hand side. And we have to support the prefix matching. So using typing and arities, we can see if applied variable can match the prefix, and we have to support that. So I have shown you one of the algorithms that we had to generalize. Now let's see how normal ATPs use these algorithms. So a lot of times,
So is it the most general unifier? Or?
yeah. So here the unification is decidable because you can basically embed everything in first order logic. So if you find the same unifiers as the first order logic unification algorithm would, if you would give it applicative encoding. So we have no lambdas, and now this is decidable, and this is the most general unifier. So ATP during a lot of during the proof search would check for a lot of terms whether they are matchable or unifiable. But not only that, a lot of times it needs to check this for the subterms. So it would check for the 2 terms head-on, and now traverse their subterms. But we have a problem that in lambda-free hierarchical logic, the number of subterms is twice as much as in first order logic. So as you can see, we have those argument subterms that we had in first order logic, but we also have the subterms that appear as prefixes. So all of those prefixes are correct subterms. And this problem could be very easily solvable by just saying, okay, I will create all those subterms and I will run my unification and matching algorithm on all of those. However, this would be terribly inefficient. So we came up with this optimization that uses the fact that given 2 terms, we know that there is at most 1 prefix using type binarity information. There is at most 1 prefix that can be unified or matched with. And then we can traverse on the argument subterms and report to the caller that maybe a prefix subterm has been matched. So let's see an example of that. So suppose that I have a unified term fxy and term fabc. Obviously, they're not unifiable head-on, but fxy is unifiable with a prefix of fabc, and the unification matching algorithms and all the other data structures, they work in this mode. They tell the caller that they don't report the failure to the caller. They just say, well, there is 1 argument trailing, there is 1 argument remaining. See what you can do with this. So you perform the inference not with a whole term, but you perform the inference with a prefix of the term. And what is important here is that no prefixes have been created. Just the information has been given to the caller that this prefix matching has occurred. So the advantages is that we consider 2 times the subterms, they create no unnecessary subterms, and there are no changes to E-term traversal loops. In other advanced things that have to be generalized were the indexing data structures, and their role is, so you're given a set of terms, and in this set of terms, you have to quickly return the terms that satisfy certain retrieval condition. And those retrieval conditions might be, well, give me all of the generalizations of the term, or give me the terms that are instances of my query term, or give me terms that are unifiable. E uses quite some indexing data structures, both for forward and backward invariances, and we have to generalize all of them. But today I will talk about discrimination trees. So discrimination trees use the idea that a lot of terms in this set are going to share structure in a certain way. And as you have seen, the unification algorithm traverses the term and does some operations, and we would like to factor out the operations that are the same for all of those terms in the set and do them only once. And how can we do that? Well, we can flatten the term, and so flatten the term to the string, and represent it as a string, and now try to generalize the string indexing techniques. And how do we flatten the term? Well, we just do pre-order left to right traversal of the term, or well, we just drop parentheses and commas. And now let's see how discrimination trees work. So suppose that this is our query term, and this is the discrimination tree. So discrimination tree works as a trie for terms represented as strings, and it has very simple idea. So if we want to look for generalizations, what we have to follow in this tree is edges labeled, so nodes labeled with the same term head as the query term, or variables that can basically match anything. So here we follow f, we have no choice, but here we do have a choice. We can either bind x to g of a, or follow g and go deeper into the term. So let's suppose we follow g. Now we bind x to a, we have no choice, and we have our own term. No neighbor can generalize the term, so we have to backtrack. In the first place, where we made a choice, which is not this. We have to backtrack further. And the first place where we had where we could make a choice was here. We have to bind x to g of a, and then go deeper in the term. We follow, we match I with I, and bind y to a, and we have found the generalization. So what were the challenges we had when we generalized this to lambda-free parallel logic? Well, the first one was applied variables. So applied variables can match a prefix of the term. So previously you have seen that we either go deeper in the term, or we match a variable with an argument and then move to the next argument. So in the pre-order traversal, we either go one step down, or we either ignore the whole subtree. Applied variables generalize this a little bit, so I can move any number of arguments because applied variable can match any number of arguments respecting typing constraints. So x can match g of a, and now I have b left that I have to match. So this complicated scheme of backtracking and moving to this tree is even further complicated with applied variables. In first-order logic, since function symbol is always applied to the same number of arguments, terms are stored only at leaves. In lambda-free order logic, this is no longer true. Terms are stored. Terms can be stored anywhere, and we have this prefix optimization, which tells that as soon as I find a term that generalizes a prefix of the term, I have to return this information. So I'm showing you some of the algorithms and data structures that we had to generalize and the optimizations that we found on our way there. But let's see how well this performs in practice. And so I would just give a small note that our prover can be compiled in two modes: as ho, which gives support for first-order logic, and fo that behaves pretty much as original E. So what was the gain on lambda-free higher-order problems? Well, we fed ho with original TP-TP problems in first order in higher-order syntax, and we fed original E with ab-encoded problems, and on almost all of those, ho was faster. And in this scatter plot, what you can see is that for the problems that are harder, ho was significantly faster. let's see some other statistics. So they both finished on 872 out of 995 problems. However, he had advantage in finding 11 unique solutions, where Ho found only 8 unique solutions. And we suspect that this is to term orderings and to the fact that since E doesn't support polymorphism, this applied variable symbol has many variations for many types, and this can give some information to heuristics. So we are still looking into that, whereas for us, we don't have this feature. The mean runtime is different just by 3 milliseconds, but because Ho is significantly faster and harder problems, the total runtime was around 17 seconds for Ho when all of the problems were both finished, whereas for applicative encoding it was in the range of 100 seconds. Another important thing that we wanted to minimize as much as we can was the overhead on the first-order reasoning core, and this is the reason why we actually support a compilation in 2 modes. We want existing key users that are not interested in going higher order to have the same behavior as they had before. And we tested this on almost 8,000 PPTV problems. The results were that the median runtime increased only for 100 milliseconds, and the total runtime was increased in something close to 2,000 seconds. But what you can see is that due to the fact that we had to generalize, for example, the type module, which I didn't cover today, we have some constant overhead that is added to the problems that are solved very fast. And you can see this here. But the problems that are hard, they take the same time. So the problems that take more than a second to solve take almost the same time. And Ho, which supports non-free hardware logic, is a little bit slower, but so the median runtime increases by 200 milliseconds, but not significantly. So in summary, from the engineering viewpoint, we have shown how to elegantly generalize first-order theorem prover to a fragment of higher-order logic, and we changed some modules completely. So for example, type module that E previously had, E supported many sorts of first-order logic, had to be changed completely, and almost all of the algorithms from inputs to outputs had to be changed. And from the theoretical viewpoint, we gave algorithms and extensions of algorithms and data structures that are graceful, which means that they do work in this richer logic, but when they are fed with first-order terms, they behave the same way they behaved before. So, and future work is integration with official E and adding new features. So here we support non-free hardware logic, and what we want to support, similarly to what's been done with Vampire, is to support first-class booleans. So to feature support for functions for logical formulas being applied to being supplied to predicates. And we also want to find ways to work with lambdas, so to encode them or to work with them natively, and in the end to reach the full hierarchy prover by extending it feature by feature. Thank you for your attention.
What is the benefit if you have, for example, tetramer for encoding into non-free hardware logic? Is it a lot easier?
So yeah. So my supervisor is just kind of lashed it, so we talked about it, right? So this is one of the most important aspects of this project, right? So right now, the difference is that Ho is going to be is going to perform faster, but when we go further, Ho is going to support more and more features, and the performance of Sledgehammer should be improved more.
So actually two. The first one is about the notion of lambda free fall. I was a bit puzzled when I saw that the first time, because you can argue that there's a notion of lambda free fall already out there. Most of us have studied higher order logic without lambda, but with full extensionality. You mentioned that as a challenge, and with full comprehension. What you actually have here is a notion of all with no Boolean extensionality and with nearly no comprehension. The question is now exactly what amount of comprehension do you have in your system? because I would puzzled about this typical example for higher order unification. Uli mentioned. I just write it.
Two more than you have three.
Yeah, I mean, this here is kind of puzzling. X applied to f of a equals f of x applied to a. This has infinitely many solutions. You have the projection, but you can also plug in arbitrary many f's for the f. Your algorithm only finds exactly one f, right? So why are you not looking for the other f's? That has nothing to do, I think, with the volume number.
Right.
So what's the semantics?
So the semantics can be totally converted to first order semantics, right? So there is so we can totally embed this in first order and reason there. But the goal here was to do this more efficient and to have a stepping stone to something in the future.
But it would be very good to have a precise semantics, because if now others are interested and want to plug in this word in their work, then you have to know what it means if you get, counter models, and if they say you have to bound for that reference, so you have to understand semantically what the exact
So this is like a role of omitting the occur check, right? This is
it's something like that. So very interesting work and very useful. It's the right direction to go, but it would be very useful to say exactly what amount of comprehension is in there to understand these kind of questions.
Yeah, so right now what I can answer to you is that, yeah, you're right. So we essentially X only with that. And this is what would have been done in implicit encoding in first order logic. So the semantics is completely first order logic.
You get a different problem if you specify different parity for X, right?
So yeah, if X will not be supplied to one argument, then we push it. So if X type is such that it can be, this has to type check also. So type of X has to be the same as type of F. So if F would take only one argument, but X would take multiple, I don't think this first would type check, but suppose we had this situation, then we couldn't match X with F.
So, Chris, I think isn't it right that to get many unifiers, X can't be typed, X is untyped?
No. You get infinitely many solutions for that. And again, it's just a function from I to I. We are regular types. This is something of type I. This is an X is an I to I, and F is also I to I. Okay? So that's typing in simple types. And again, the instantiations here are simply terms like under X, F of X.
in the beginning, you had the choice doing it a pre-compilation with the apply operator or doing it your way. I mean, would be a nice experiment to see how the figures are looking like if you do a pre-compilation.
Yeah, so yeah, so we did for original E. When we tested original E, was fed with applicative encoding.
Okay.
So it is the programs have been encoded when we tested.
So I was wondering if you take at least some DHF problems, and see whether, even if you initially don't know whether they lie in this fragment, you just run this on them and you get some solutions, hopefully.
Yeah, so this is almost the way we did it. So we took teacher prompts for TPTP, but we encoded them in a way that we do not have symbols that return a pool. We encode them in our own pool and then have typecasts at the very end. Because we don't support Boolean exceptionality and we cannot give logical formulas to predicates. So we encoded this as so for some problems that do have predicate symbols, we encoded them via typecasting. So we said, okay, they are not predicate symbols; they return some arbitrary type, and then at the end we typecasted everything. So and this is how we got to 991 problems. Otherwise, we.
Oh, I see. So this is taken from THF.
This is taken from TPTP, yeah, from THF.
Okay.
Kind of like exactly like.
Sorry. Yeah.
Yeah,
I thought that you basically always used FOF from THF. Okay.
I see no more questions, so I guess we'll move to coffee break then.